City College, and my mentor for this project was Professor Gautam Chinta. He's a professor at City College. And the project that we worked on was entitled Questions in the Distribution of Prime Numbers. Now, I know a lot of people tend to get frightened with mathematics, but bear with me, I'll try and make this as simple and as painless as possible. And just hold your questions till the end, and I'll answer them to the best of my ability. So, first, we have to define, well, what is a prime number? So, prime number is, a rational prime number is any number greater than 0 whose only proper divisors are itself and 1. Proper here meaning our quotient also belongs to the set of rational numbers. And prime numbers are also the building blocks of all real numbers. All integers can be uniquely expressed as the product of prime numbers. So, for example, 100 we can express as 2 squared times 5 squared, where 2 and 5 are our prime numbers. So, knowing this, several questions naturally arise. First, how do you decide if a number is prime? And if it's not prime, how do you factor it into its prime components? So answering our first question, we ask, so is there some number p that divides our so-called prime, we'll call it thing? So for example, taking the number 299, we ask, is there some p that divides 299? So we test using our list of known primes. So we test, is 2 divided, is 3 divided, is 5 divided? Another question arises, do we just go on forever testing all the primes? Where do we stop testing? So what we do is we say, well, if our number isn't prime, we can write it as the product of 2 numbers, here p times d, where p is the smaller of our 2 factors. So taking that inequality here, p times d, what we do is we multiply both sides by p. So on one side we have p times d, and on the other side we have p times p, which is p squared. And if you recall, before we defined 299 as p times d, so we go ahead and replace it there. So we say that 299 is greater than or equal to p squared. Or we can solve for p and say that p is less than or equal to the square root of 299, or generic terms. We only need to test up to the square root of our number. So the square root of 299 is just about 17, so we continue testing. We ask 7 divided, 11 divided, up until we get to 13. We find that 13 does divide 299. And in fact, 13 times 23 is 299. So looking at this, we ask, is this the only way to actually test the primality of a number? Because, I mean, it is pretty tedious going through the list of every known prime. So is this really the only way? And the answer to that is no. Another method is using what we call the sieve of Eratosthenes. Now what this is, it's just a fancy name for a technique to quickly generate a list of all the primes less than a certain number. So for this example, I'm only going up to the number 20. So to use this method, first what we do is we cross off number 1, because 1 is the prime. And then we go on to our next number, here, 2. And then we go and we cross off all of the multiples of 2. So we cross off 4, 6, 8, 10, 12, 14, 16, 18, and 20. And then we move on to our next number, here, 3. And we cross off all of its multiples. 6 is already crossed off. We cross off 9. 12 is already crossed off. We cross off 15. And then we crossed off all multiples of 3. And then the same rule applies here. We only need to test up the square root of our largest number. So the square root of 20 falls between 4 and 5. 4 is already crossed off. So once we cross off the multiples of 3, we've crossed off all the multiples, and all the numbers that are left are prime numbers. So in this case, 2, 3, 5, 7, 11, 13, 17, and 19. So that's another quick way of quickly generating this primes. Now, our is a program that we use to calculate pretty repetitive and tedious tasks. It really helped ease the actual amount of calculations that we had to do by hand. We could just write a script that Puri could follow, and just leave it to do its calculations, and then come back once it was done. Just review our data. So one of the major points of any research is to verify the work of, well, in our case, that other mathematicians have done. So we verified the work of 2 people by the name of Andrew Granville and Greg Martin in their research paper entitled Prime Number Races. So what they did is they took the list of all rational primes and they divided it into 2 categories using modular arithmetic. And for those of you unfamiliar with modular arithmetic, it's very similar to regular division, except in division we're more concerned with quotient, and in modular arithmetic we're more concerned with our remainder. So what that means is, take for example, 6 divided by 2. 6 divided by 2 is 3, remainder 0. So normally we'd be more concerned with the 3. But in modular arithmetic, because we have a remainder of 0 when we take 6 and divide it by 2, we say that 6 is congruent to 0 mod 2 because we have a remainder of 0. If we take 5 and divide it by 4, we say that 5 is congruent to 1 mod 4 because 5 gives us a remainder of 1 when we divide by 4. So using this technique, whenever you divide something by 4, there's always 4 possible remainders. You either have a remainder of 0, meaning that the number we're dividing was a multiple of 4. We have a remainder of 2, which means our divisor was an even number, and the only even prime number is 2. So that leaves us with just a possible remainder of 1 or 3 when we're dividing prime numbers. So for example, 3 divided by 4 is 0, remainder of 3, falls into category 3 mod 4, 5, remainder of 1 falls into 1 mod 4. So it turns out that the prime numbers are more or less evenly divided into these two categories, but there is, however, a tendency towards 3 mod 4 over 1. And it turns out that 3 mod 4 is in the lead just about 99% of the time as our number of primes approach infinity. And a similar winning of some categories over others also holds true for other mod divisors. So we tried this with mod 3, mod 5, mod 6, and so on. And the losers of any prime number race are congruent to some square number mod n. So what that means is, for the case of, say, mod 4, 3 squared, which is 9, mod 4 is congruent to 1 mod 4, so that's why 1 mod 4 was a loser in the race of 1 mod 4 and 3 mod 4. So our current research is taking that whole notion of the prime number races and applying it to entirely different sets of numbers. So the sets of numbers that we worked with were what are called Gaussian integers. And Gaussian integers are numbers of the form a plus bi, and for those of you who are familiar with it, they're also known as complex numbers. So, for example, number 2 plus 3i or 6 minus 8i would be considered Gaussian integers. They're just our standard complex numbers. So the same Gaussian integers also have this notion of primes. However, when we're dealing with Gaussian integers, Gaussian primes are integers whose only proper divisors are plus or minus 1, plus or minus I, and multiples of itself by plus or minus 1, plus or minus I. So what that means is, if you take the number 1 plus 2i, we can write it as negative 1 times negative 1 minus 2i, or I times 2 minus I. But these aren't particularly meaningful, so we say that 1 plus 2i is a prime. Also, the same notion of factoring applies here, just like with rational primes. Either an integer is a prime or factoring it gives us primes. So either a Gaussian integer is a prime or factoring it gives us a Gaussian prime. So certain rational primes may also be considered complex primes as well. So only primes of the form x squared plus y squared, where x and y are rational numbers. Only primes of that form can be factored into Gaussian primes. So in other words, if you can take a prime number and write it as the sum of 2 squares, then it's not a Gaussian prime and it can be factorable. So for example, take the number 5, which is a rational prime. We can write it as 4 plus 1, which is 2 squared plus 1 squared. And because we can write it in that form, the sum of 2 squares, we can further expand it into a complex number. So we can take 2 squared plus 1 squared and write it as 2 plus I and 2 minus I. So because we can write it in that form, 5 isn't a Gaussian prime, but factoring it gives us the Gaussian primes, 2 plus I and 2 minus I. But if we take the number 7, which is also a rational prime, we can't write it in the form as the sum of 2 squares, so we say that 7 is